Review problem 4 is a system of connected objects. And we have learned that you can do this type of problem the long way, or you can do it the really quick way. And I don't want to do it the long way. So let's talk about how to do it using the shortcut. In a problem like this, you identify the system, and then you can write down the acceleration as being the external forces acting on that system divided by the mass of the system. So I'm gonna write this equation out in words and then eventually put in expressions. The acceleration of the system is the net external force acting on it divided by the mass of the system. So our system consists of these two masses, M1 and M2, and the string connecting them. The string is massless, so we don't need to include its mass. The string has a tension force in it, but that tension force is an internal force in the system. It's not an external force to the system. So we don't need to worry about that tension force when we're calculating the acceleration. We will figure out the tension force in part B, where we just look at a single object as being a system. That makes the string external to that single mass, and then we can figure out the tension force. But in part A, our system is mass 1, the string, and mass 2. So what we'll do is we'll identify all the external forces acting on the system. And the ones that, the forces that tend to make the system speed up, we'll give those a positive sign. And the forces that tend to make the system slow down, we'll get a negative sign. Now in this configuration, there's only one force that's going to make the system speed up. And that is the gravity force pulling on M2. Nothing else will make the system go faster. Only gravity on M2. Gravity acting on M1 doesn't really have any effect because it's pointing straight down. But gravity on M2 points straight down, but there's a component along the slope. It's a cat. Okay, so let's write down that gravity force on mass 2. Or, sorry, we'll get to that in just a minute. I'm still writing out the words for these things. So we have a positive force, that's gravity on M2. That'll make things go. And then we have two forces that are going to slow the system down. That's the friction force on each of these objects. And again, the total mass of the system. All right, so now that we've written this equation in words, we need to fill in mathematical expressions for all these things. And we do this by drawing on our semester's worth of experience doing Newton's second law problems. The gravity force on M2, well, M2 is on a slope, and we've seen these slope problems before. The gravity force is M2g sine theta. friction force on M1. M1 is on a horizontal flat surface. Friction force is coefficient of friction times normal force. We know that the normal force in this case on a flat surface is just the weight of M1. So we've got the coefficient of friction, mu K for aluminum. M1 is made of aluminum. It's pressed against steel, and the problem gives you this value of kinetic friction for aluminum on steel. I'll write mu K Al for aluminum times M1G. M1G is the normal force on it. M2 has a friction force as well. Its coefficient times normal force. Its coefficient is mu of copper on steel, Cu for copper. And its normal force is slightly more complicated because it's on a slope. We know from experience, having done slope problems, that the normal force gets cosine of this angle. And the total mass of the system is M1 plus M2. The string is part of the system, but we assume that it's massless. And there's your answer. Our problem-solving process for obtaining this answer wasn't to draw free body diagrams and solve systems of equations. It was to use some common sense, look at the picture, identify forces that are making the system go, forces that are slowing the system down, and then drawing on our past experience of having solved many problems before to write down the mathematical expressions for each of those forces. So something I might ask you to do on the exam is explain this process in words like I just did now. Tell me what each of these terms mean and how you knew to write them in the equation. Okay, part B. What's the tension in the strain? What's the tension force? So we can solve this by now considering, say, just M1 as the whole system of interest. And now the string will be external to that system. And we can now identify the force it provides. We could also do this by considering M2, but that'll be a little bit harder to do. It'll be a more complicated free body diagram. So I'm picking the easier way. So let's draw a free body diagram for M1. M1 is now our entire system in part B. M1 is experiencing this tension force to the right. It's experiencing a friction force to the left. It's experiencing gravity down and normal force up. When you do Newton's second law in the y direction, that analysis will tell you that the normal force equals the weight. We've done that many times. That's because this is horizontal, it's not on a slope. In the x direction, so that's M1. In the x direction we have tension minus friction force equals M1A. So tension equals friction force plus M1A. and that friction force equals mu K AL for aluminum times the normal force, which was M1G plus M1A. We already found A, the acceleration, in the previous part of the problem. So now we know how much tension force that string is providing.